We're going to resume our activities for today, and we have the online talk by Professor Julian Barbour. It's a pleasure to have him here. Professor Barbour is a theoretical physicist. He's an author, and he has worked on foundational issues in physics for nearly 50 years, specializing in the study of time and motion. He is emeritus visiting professor in physics at the University of Oxford. He has many papers, many important contributions to science. So I will just leave you with a talk by Professor Barbour. Thank you, Professor.
All right. Should I start?
Yes, please.
Right. I wish I were with you today. I think Henrique Gomez is. He sharpened my understanding of gauge theory during several visits to my home north of Oxford about 20 years ago. You see me in the image at the back door of my house, built in 1659. In the summer, swifts, faster in level flight than any other bird, nest under its tiles. Henrique was one of a group of us who developed the theory of shape dynamics. You will see the motto Forma Formosa, beautiful shape. It is interesting that the Latin languages have just the word forma, whereas English, which takes words from Latin and German, has both form and shape. There's a passage near the end of Shakespeare's A Midsummer Night's Dream in which Theseus dismisses the accounts of the lover's nocturnal experiences in the forest as imaginations like those of the lunatic, the lover, and the poet, adding that the poet's eye, in fine frenzy rolling, doth glance from heaven to earth, from earth to heaven, and as imagination bodies forth the forms of things unknown, the poet's pen turns them to shapes and gives to airy nothing a local habitation and a name. It is clear that for Shakespeare, a shape was more special or sharply defined than a form. The existence of the two words in English makes it impossible to render Shakespeare's distinction into the Latin languages except by circumlocution. It highlights the importance of word choice. I would like to give an example for that. Back in 1999, aiming to liberate dynamics from the straitjacket of Newton's absolute space and time, I defined, for finitely many particles with given mass ratios, shape space as the analog of the Newtonian configuration space, but for the possible shapes that the points can define. Next slide, please. Shape space is therefore the quotient of the configuration space with respect to the similarity group, which contains translational and rotational transformations, but also, and most importantly, dilatations. These extra transformations have been almost completely ignored in physics. Most of my talk will be about what happens to key concepts when scale invariance is taken to be the most important symmetry of all. My reason for introducing shape space was to characterize how shapes, taken to define a universe, would change. I called that shape dynamics. I could never have called it form dynamics. That just does not sound right. I hope you will soon understand why. The background will help. In 1977, I read some philosophical writings of Leibniz, the central observation of which, obvious once noted, is that without variety in the world, we would know nothing. There would be nothing. Leibniz believed God must want perfection and aim to create a universe with the greatest possible variety. However, Leibniz never made up his mind whether God would make a universe maximally varied through all eternity, or one that becomes ever more varied. My talk is about a law that makes the variety of the universe increase forever. My collaborators and I stumbled on it 4 years ago. In it, the distinction between shape and size is critical. It illustrates the need for scale invariance. Consider first any triangle. It will have a shape that its internal angles define and a size that can be increased or decreased without changing the angles. They are scale invariant. The same distinction exists for any number of points distributed in Euclidean space. From any point, the lines to any two other make an angle. Overall, expansion will not change any of those angles. It is often forgotten, or not even realized, that within any system, only angles are observable. Size presupposes an external ruler and has no objective meaning within the system. We never see anything but ratios. You see that my eyes are smaller than my head than my body than the room in which I'm speaking, which in turn is smaller than the house of which it is part. Nowhere in the universe can you find a magnitude that is not a ratio. I joke that the inscription on my tombstone should be "Nothing but ratios." With that background, consider 3 or more points in space. What scale invariant number characterizes the extent to which they are uniformly distributed or clustered? To be scale invariant, it must have length dimension 0. That is readily achieved by making it the ratio of 2 numbers that the complete set of points define and each have length dimension 1. Mathematically, 2 such numbers are distinguished. Next slide, please. For 3 points separated by distances A, B, and C, and the dots if there are more, they appear in the expression on the slide. The first term is the root mean square length, while the second is the inverse of the mean harmonic length. The normalization by the number of terms cancels. The variety is manifestly a scale invariant ratio. I should say that my collaborators and I originally called it the complexity, but since Leibniz's philosophy was its midwife and complexity is used for so many other notions, I now think variety is better. As a ratio, the variety has an important property. For any nominal scale used to define distances, and with them an extrinsic scale of the system, the large separations dominate the first factor and the short ones the second. Thus, except for a fractional residual, the variety is the number of times a shorter length fits into a longer one. This is exactly what happens in measurement. The variety is the intrinsic scale within the universe that the points define. It is a measure of size. I was once on a radio program in Britain about cosmology with the astrophysicist Martin Rees, at that time the president of the Royal Society. At some point, I said the universe is not expanding, but changing its shape. Martin Rees's response was, "Julian, your philosophy may be good, but I think you are forgetting 90% of the physics." At that time, all I knew was that the successive shapes of a Newtonian universe in the form of the n-body problem contain all the objective information about its history. Its evolution is expressed as change of shape. That was my philosophical argument. However, I had not yet come across the expression for the variety. 9 years later, in 2011, I did. I learned from specialists that, with sign reversed, it plays a central role in the Newtonian n-body problem and is called the shape potential or normalized Newton potential. To explain why, let me call the points particles and, as in the second expression, give them Cartesian coordinates and masses that are a fraction of a nominal unit total mass. The first term in the variety then becomes the mass-weighted measure of the size of any Newtonian n-body system. The second is the Newton potential. The minus sign is purely nominal. Already here, some comments are in order. First, everything of interest already holds for equal mass particles. They, like particles with different masses, can be treated, as in my heuristic derivation of the variety, as points with zero size. Second, the zero size of points, with or without mass, makes satisfaction of scale invariance and formation of structures in the form of clusters of points trivial. I find it hard to imagine a simpler ontology that is capable of modeling our experience of structures around us and in the universe at large. In contrast, in a classical field theory, it is very difficult to model bodies as localized concentrations of energy. It can just about be done in general relativity with a geon, which is a non-singular electromagnetic or gravitational wave held together in a confined region by the gravitational attraction of its own field energy. However, that is not yet a scale-invariant object, since it is defined in terms of proper distance, which, in presupposing an external ruler, is not a scale-invariant concept. I suspect modeling the ubiquitous bodies we see around us by a scale-invariant field distribution is simply impossible. In contrast, creating localized structures among an infinite number of points that are more or less uniformly distributed in infinite space is trivial. You simply make clusters of points. One of them could look like Orion on a clear, dark night. The variety can also be defined for any localized cluster of points within any larger, even infinite number of them. That will be important when I come to the age half of my talk, which I will do after size. But first, my third and final comment. The simplest way to define the variety of points in space, which Leibniz himself could have proposed, leads directly to the two functions that define the oldest mathematically precise dynamical theory, the n-body problem of Isaac Newton's theory of universal gravitation, simply defining how particle separations change in a scale-invariant manner by means of two functions, nothing more, nothing less, unifies the aspirations of those two bitter enemies, as in the next slide, please. Now I come to the size half of my title and how it can change. I already said that the variety is an intrinsic measure of size. It is what beings within a universe of points could observe. As the shape of their distribution changes, so will the variety. Important here are the properties that the variety has besides scale invariance. It is positive definite, has a unique absolute minimum, and no upper bound. My aim when I introduced shape space was, as I said, to represent n-body solutions in it. In that space, they become undirected, unparametrized curves that represent a succession of shapes. The projection reduces everything to the essential minimum. No critical information is lost. All redundancy is eliminated. The possible paths the solutions can take reveal much. They show that Newton corrupted his greatest discovery, his second law of motion. I will illustrate that claim with equal mass points, which suffice to show the damage Newton inflicted when he introduced absolute time and absolute space as the framework of dynamics. Mere points in Euclidean space enable me to define, by analogy with the normalized Newton potential, normalized separations between n points. Next slide, please. If Rij is the distance between points I and j, then their normalized separation is Rij divided by the root mean square length of the n points. Now suppose two distributions of points whose normalized separations differ infinitesimally. Between the two distributions, there is therefore an undeniable difference. Newton's absolutes play no role in its definition, but they do in the application of Newton's second law, which requires initial conditions that reflect the infinitesimal change of the system's configuration in an infinitesimal amount of time. The problem is that many different initial conditions, all leading to quite different subsequent evolutions, are compatible with any particular undeniable difference. The first ambiguity is that there is no indication of whether the R1s or the R2s come first in time. I will come to that in a moment. What really creates ambiguity is the existence of the two sets of data, the R1s and the R2s. Were there only one, say the R1, the shape that it defines could be represented as a configuration with an overall scale in an arbitrary Cartesian coordinate system with center of mass at the origin and at initial time t equals 0. All these choices would be purely nominal. But then come three real problems. First, what is the unknown infinitesimal time delta t between the two shapes? Second, what is their relative orientation? Third, what ratio of scales is to be associated with the two configurations corresponding to them? All three of these problems must be resolved if we are to define Newtonian initial data. Since the initial potential energy is fixed by the nominal scale chosen for the first shape, the first problem means one has no information about the velocities and with them the total energy in the system. The second problem is that one has no information about the angular momentum in the system. And the third, that the proportion of energy in overall expansion is unknown. The fact that the position of the center of mass of the second configuration relative to that of the first is unknown is not serious, since Galilean invariance allows one to work in the center of mass frame. the relational arguments against absolute time and space that first Leibniz and then Ernst Mach raised allow one to argue that the only allowed solutions must, in Newtonian terms, have vanishing values of their total energy and angular momentum, as specified in the slide. As regards the third problem, there is an analogue of angular momentum in which the cross product is replaced by the dot product, as also in the slide. Although the corresponding quantity has played an important role in the n-body theory for 250 years, and is the quantity used for about 150 years in the derivation of the virial theorem in statistical mechanics, it had never been given a name until I called it the dilatational momentum in a paper in 2003. It probably failed to get a name for so long because it is not conserved under potentials like the Newton potential, which are homogeneous of degree -1, but only under a potential homogeneous of degree -2, and such potentials do not help with the elimination of Newton's corruption of his own theory. There is a different solution to the problem, which I will give in a moment. At this point, it will help to give you an idea of how the projections of all Newtonian n-body solutions to shape space behave. A set of them of non-vanishing measure with negative energy do nothing particularly interesting. They do not have any special asymptotic behavior and simply wander around shape space. However, most negative energy solutions behave like more interesting solutions with energy that is either zero or positive, and I will now describe. Except for solutions that belong to a set of measure zero that are the most interesting, and to which I will come, all the rest have what I call a Janus point. At it, the extrinsic scale that the root mean square length defines passes through a non-vanishing minimum on either side of which it increases monotonically to infinity. Lagrange proved this for the three-body problem as the first qualitative result in dynamics in 1772. Jacobi later extended the proof to the n-body problem. More interesting than this property of the extrinsic scale is that in the vicinity of the Janus point, the distribution of the particles is more uniform than anywhere else, and therefore the variety, the measure of intrinsic scale, is at a minimum and then undergoes secular increase with fluctuations that become progressively smaller in relative magnitude as the curve on both sides of the Janus point tends to points in shape space at which the variety becomes infinite and act as attractors. As Tim Kozlowski, Flavio Mercati, and I were the first to point out in this paper, next slide please, in 2014, these solutions have bidirectional arrows of time with behavior that is the exact opposite of entropic arrows. The next slide, shown please, this is our figure in the paper showing how the variety, called complexity in that paper, increases either side of the Janus point. In the exact opposite of thermodynamic increase of entropy, in these solutions, order emerges out of chaotic, disordered motion. To be precise about the actual form of the ordered motion, I recall Dirac's distinction between Hamiltonian and constrained Hamiltonian systems in his important book, next slide please, Lectures on Quantum Mechanics of 1964. Simple examples of constrained systems, not given by Dirac, are the n-body solutions with vanishing total energy and angular momentum as constraints. For such systems, one cannot specify initial data freely. The data must satisfy the constraints. In the n-body problem, the constraints are global, and data that satisfy them are easily found. In contrast, Dirac had field theories in mind, for which the constraints are local and significantly harder to satisfy, since they require the solution of elliptical partial differential equations. In order of difficulty, they are the Gauss constraint in electromagnetism, the constraints that arise in non-abelian gauge theories, and, hardest of all, the linear and quadratic constraints in general relativity. I do not need to discuss them. I merely want to put what I am now going to say in context, which is that if the n-body solutions that satisfy the constraints of vanishing energy and angular momentum are taken to be those of a model universe, then throughout its history, constrained Hamiltonian dynamics governs its behavior. But on each side of the Janus point, in the direction away from it, the complete universe breaks up into subsystems that exist for a certain length of time, but eventually break up into single particles or pairs of particles. The singletons tend to move inertially with ever better accuracy and hence satisfy Newton's first law, while the pairs orbit their common center of mass in Keplerian ellipses with ever better accuracy, and through their periods and lengths and directions of their major axes, each becomes a rod, clock, and compass, all in one, and all of these systems synchronize their behavior ever better. In such solutions, which I call Machian, a non-entropic arrow of time is strikingly manifested in the emergence out of the constrained Hamiltonian law of the universe of the subsystems that satisfy local laws of nature that are Hamiltonian. I therefore question whether we should seek laws of nature that have universal applicability for all time. I conjecture rather that a single overarching law governs the universe as a whole, and that what we take to be laws of nature are approximate local regularity, including those of thermodynamics, which arise at different times and govern subsystems in different regions. In the Newtonian model, the subsystems can have all possible values of their energy, angular momentum, and momentum, provided the sums for the complete universe are all exactly zero. There is a beautiful realization of the effect in the n-body problem with vanishing energy and angular momentum, as illustrated in the next figure, please. In every solution in whichever way time is assumed to flow, there is a Kepler pair in the distant past that approaches the three-particle center of mass and a single particle coming in the opposite direction toward it. The shape that the three particles define is divided almost completely into two halves, the pair and the singleton, each of which satisfy Newton's laws to very good but not perfect accuracy. However, as the two subsystems approach each other, the inevitable three-particle interaction first destroys the two existing systems and then creates two new ones, possibly with a swapping of partners and always a change of orbital elements of whatever pair emerges. The image bottom right in the figure shows how the shape changes on a shape sphere that I will discuss at the end. Since the discovery of the laws of thermodynamics, the existence of an arrow of time has been associated with the second law and the inevitable growth of entropy that it predicts. In the context of a physical system in a box with a small ice cube that is initially present before melting into water, whose molecules then spread out to fill the whole box in the equilibrium state of maximal entropy, that all seems to make sense until one asks how the initially highly ordered ice state can have arisen, and more seriously, why, despite the second law, the universe is manifestly very far from equilibrium. Already Boltzmann suggested that, for some unknown reason, the universe might have had a very low entropy in the past. Feynman first stated this explicitly in 1964, saying that to explain why the current universe is so far from equilibrium, it is necessary to add to the known laws of nature something extra in the form of a low entropy condition in the past for which no known explanation exists. David Albert later called the assumption the past hypothesis, though of course giving the problem a name does not solve it. Despite this great puzzle and the deus ex machina that must be invoked to save the second law, faith in it is remarkably strong and was expressed most memorably by Arthur Eddington in 1927, who said, "The law that entropy always increases holds, I think, the supreme position among the laws of nature. If your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation." This prompts the question of whether the n-body solutions I have described are the basis on which the problem of time's arrow can be finally solved 170 years after Helmholtz said that the universe is condemned to die in heat death. Nothing is ever certain in science, but I do think our result at least highlights a remarkable failure among theoreticians to consider the conditions under which the laws of thermodynamics can be expected to hold. For this, one has to recall that it was Sadi Carnot, slide 11, his wonderful study of steam engine efficiency in 1824 that led eventually to the discovery of the second law. Carnot already showed that in continuous operation of a steam engine, some heat will always be lost. The first clear formulation of the second law came 26 years later, but so far as I know, nobody pointed out something even more fundamental than maximal efficiency. It is that a steam engine stops and does not run at all if the steam escapes from its cylinder. Although, to my knowledge, this simple fact was never recognized explicitly in all the studies, both experimental and theoretical, that created the seemingly impregnable fortress of thermodynamics and statistical mechanics, above all the second law, it was always assumed implicitly in the theoretical studies and employed physically by a material container, a box, in experimental studies. The only caveat I have found is in Willard Gibbs' slide, please, next one, book on statistical mechanics of 1903. In it, he says his results will cease to hold if the considered system can become distributed in infinite space, in other words, is not in a box, or if the momenta can grow without limit. For then expressed in terms of dynamical systems, their solutions will be able to explore a phase space of unbounded Liouville measure, and in Gibbs's explicit words, the coefficient of probability vanishes and the law of distribution becomes illusory. By that, Gibbs meant conservation of phase space volume. It becomes illusory. Gibbs does not say anything of whether anything of interest might be deduced under such conditions. Now, both conditions under which Gibbs said his theory will fail occur in the n-body problem, the oldest, non-trivial, and rigorously defined dynamical theory. In it, we certainly obtained a rigorous result and a non-entropic explanation of time's arrow. From this, I draw the conclusion that mere longevity of a result in science does not mean it has universal validity. In fact, conditions under which it is not may be blindingly obvious once they have been pointed out. Note also that the scale invariance of the variety is most important and suggestive. First, it identifies the mathematically defined quantity, much more precisely than entropy, that increases, and second, draws attention to three-dimensional scale invariance, a symmetry whose implications have been remarkably ignored. This brings me to the zero-measure set of solutions that I said have even more interest than the Janus point ones. Carl Sundman, in the next slide, please, discovered them in the three-body problem in 1907, and they were extended to arbitrary n a year later. They are called total collision solutions because in them the root mean square length, the extrinsic Newtonian scale implicit in the notion of absolute space can vanish. And that suggests that all the particles converge on a single point and collide there. However, what the mathematics actually says, and is what observers within the universe could experience, is that the variety tends to a critical point, which is either its absolute minimum, a local minimum, or a saddle. In the three-body problem, the absolute minimum is, for all mass ratios, the equilateral triangle, and there are also three saddles, these differing according to which of the three particles is between the other two. Thus, if the universe, like us, possessed proprioception, which allows us to know the relative disposition of our body parts and the ratios of their lengths without needing to look at them, in a so-called total collision, the universe would not feel it had collapsed upon itself, but had merely come into a special shape, from which, in fact, the n-body specialists have found no way to continue the solution uniquely. What is more, these solutions become Newtonian big bangs under time reversal. We no longer have a Janus point solution in which the variety or complexity, as we called it in that image, next slide please, defines bidirectional arrows of time, but just a single arrow corresponding to, say, the right half of the diagram. It points from a shape with maximal uniformity to shapes of ever-increasing variety and order. At least for the Newtonian universe, this is the exact opposite of entropic increase and heat death. It may also be noted that these Newtonian solutions were discovered mathematically 2 decades before Hubble's observations and his announcement that the universe is expanding. I may also say that in these Big Bang solutions, that third problem, which defines from Newton's absolutes, the most pernicious one of two finite values of the root mean square length, that does not arise, since in these solutions, one of the values of the root mean square length at the Big Bang is 0, and so you can't form a proper ratio with that. From this, it is clear to me that the intuition behind the word expanding is the absolute scale inherent in Newton's absolute space. I get suspicious when I hear cosmologists say, as they often do, that space itself is expanding. What we can say is that, since the Big Bang, structures, beginning with nuclei and extending all the way up to galaxies, have come into existence and from then on maintained either extremely stable ratios of their sizes, as is the case with nuclei, atoms, and molecules, less stable but long-lasting ratios in the case of stars, and even less stable ratios in the case of galaxies. In comparison, what does not stay stable, but does increase, is the ratio of the typical intergalactic separations divided by all the other separations. Mathematically and objectively, that is a change of shape. Thus, if the Newtonian n-body problem is a good guide, and I believe it is, what is actually happening in the universe is that its variety, and with it, because they are the same thing, its intrinsic size is increasing. This brings me to the end of the part of my talk devoted to size and brings me to age, which is actually a variation on the same theme, or rather the same mathematical concepts. I cannot now recall whether it was me or my main collaborator, Tim Kozlowski, shown here in the next slide, please, with me at my home north of Oxford, who first suggested the word age, but I think it was Tim. He certainly uses it consistently as a most useful and readily understood concept. It relies on the simple fact that the variety, through being positive definite, has an absolute minimum. Now consider any finite number of particles with arbitrary mass ratios that define a shape that has a certain variety. For those same particles, there is an absolute minimum of the variety of the shapes they can form. Then Tim and I define the age of any shape that the considered particles can form as its actual variety minus the absolute minimum that it could have. This immediately establishes a direct connection between all things in the universe and the universe itself. The fundamental fact is very simple. Virtually anything that exists for any length of time in the universe becomes more richly structured as it ages. There is more variety in its structure. As a newborn baby, I had smooth skin and hardly any hair. My skin is now much rougher, and though not much, I still have more hair than at birth. The merest glance at that photo of Tim and me tells you that I am older than him and gives you a good idea of by how much. I could give you countless examples, which are legion in biology, geology, and astronomy. From the latter in particular, we know that the universe is full of stars that have a great range of ages, their age being correlated with the complexity of the nuclei within them, as the initial simple mix of hydrogen and helium is steadily enriched with heavier nuclei. Thus, the universe is the oldest thing we know and contains within it all manner of things, each and every one of them with ages that can in principle, that an analogous notion of variety can in principle define and determine. As I have introduced variety as the fundamental concept for describing the universe, it clearly presupposes a notion of simultaneity. Relativists will think this is problematic. I will not go into details, but two things, one theoretical, the other observational, suggest that despite the relativity of simultaneity, which is such an important concept in general relativity, a notion of simultaneity can be consistently and sensibly defined in the universe. The theoretical evidence comes from the structure of general relativity as a dynamical theory, as opposed to space-time that Dirac, as the first step to a quantum theory of gravity, was the first to highlight. Next slide, please. This is the first page and conclusion of his 1958 paper, in which, as you see, he was establishing the Hamiltonian form of the theory of gravitation. In the paragraph at the bottom of the first page of his paper, with the parts underlined, Dirac notes that in the theory one may choose a considered surface to be independent of the system of coordinates, and that this has the advantage of preserving the symmetry between the four coordinates. But now comes his decisive observation that this has the disadvantage of bringing in more variables than are needed for the mathematical treatment of the problem, with the result that the equations are complicated and obscure. One gets a simpler scheme by choosing the system of coordinates x mu such that the surfaces x0 equals constant are all space-like, and then considering only states on those surfaces. The symmetry between the four x's is completely destroyed, but the resulting simplification makes this sacrifice well worthwhile. I can omit the mathematical details and just quote Dirac's conclusion. He says that not all of the 10 variables that Einstein used to describe the gravitational field, only 6 remain. This, he says, is a substantial simplification, but can be obtained only by giving up four-dimensional symmetry. Clearly aware that relativists will regard this as heretical, Dirac says, I am inclined to believe from this that four-dimensional symmetry is not a fundamental property of the physical world. 5 years after his paper had been published, I came across this sentence by chance in a newspaper article about Dirac's one and only paper intended for the general public. It was published in the Scientific American in May 1963. There is no need for me to go into the story of my life since then, except to say 2 things. The first is that, given Dirac was challenging one of the most fundamental tenets of modern physics, it prompted me to ask, what is time? 62 years later, I am still seeking the answer to that question, and now think the best answer may well be to replace the notion of time by that of age, as I have defined it. The second is that in a paper a year later, Dirac proposed a specific way of defining simultaneity called maximal slicing. However, it is not in fact ideal, and a better choice is constant mean curvature slicing. I won't go into details, but it brings me to the observational aspect, which is that the microwave background defines a pragmatic definition of simultaneity that seems to agree very well with constant mean curvature slicing. For what I want to say, the important thing is that the essential core of general relativity as a dynamical theory is retained in this way, and everything that you can eliminate as redundant is eliminated. I've included this discussion of Dirac's work, which I do not think has received as much attention from experts as it should have, because the notions of variety and age that I have presented presuppose a notion of simultaneity. If you think I should not do that, I invoke Dirac in my defense. I now want to show you remarkable structures that are created by the definition of variety that I've given you. They were found almost by accident at the observatory in Paris by a Spanish student, Manuel Izquierdo, and came about because of my long interaction there at the observatory with Alain Albuy, who is a specialist in the Newtonian n-body problem. I had been discussing with him the issue of how the Newtonian Big Bang solutions begin. This is a tricky matter, although it had long been known that total collisions begin at a critical point of the variety, so that the Big Bangs, which are their time reverse, must begin at one. However, that does not fix the initial conditions, since there are no proper Cauchy data when they begin, due to the presence of an essential singularity in the behavior of the solutions. All such Big Bangs begin along eigenvectors of the shape potential, which I'm calling the variety, and the great bulk of them do so along the eigenvector with largest eigenvalue. Which solutions will emerge only becomes clear at a finite distance from the initial critical point, at which a great range of solutions peel off and evolve across the space of all possible shapes of the corresponding number of particles. These shapes, at some distance from the initial critical shape, can also be critical points with slightly larger value of the variety. So Alain suggested Manuel look for critical points, which are called central configurations or relative equilibria, with value of the variety a little bit greater than the absolute minimum, in fact about 1.5% greater. One could then attempt a kind of approximation to how a solution, once established, would evolve. What Manuel found was remarkable and is shown below his picture in the next slide, please. You see two distributions corresponding to critical shapes of 1,000 equal mass particles in 2 dimensions. The one on the left is very close to the absolute minimum, or perhaps actually at it, while the other has, as I said, a variety about 1.5% greater. That a distribution like the one on the left would exist near the absolute minimum had long been known, both theoretically and as found in numerical simulations. However, the one on the right, with its great profusion of filaments and other remarkable structures, was a complete surprise that specialists found interesting and still find difficult to explain. I am beginning to get some idea of an explanation. One thing at least is definite. Suppose the law of the universe is that its variety must increase steadily forever from the distribution on the left. One way to increase the variety is simply to move a few particles closer to each other. But if we are trying to model a universe, that will violate the cosmological principle since a localized region within it will look quite different to the rest. A moment's thought shows that there are vastly more ways to increase the variety by changing all the separations a bit, but doing so in such a way that a significant number of the shortest separations are more or less equal. Otherwise, there's danger of overshooting. This very closely matches the insight of Boltzmann that for molecules in a box, there are vastly more uniform than non-uniform distributions of them. That realization of Boltzmann led to the well-known expression S equals K log W for entropy and the prediction of the universe's heat death. In the present case, with shapes characterized by their variety, its increase governed by statistical considerations identical in nature to Boltzmann's leads to greater structure. Heat death is replaced by greater order. This is not all. A bit over a year before Manuel discovered the remarkable shapes, I had proposed a resolution to the problem of time associated with the Wheeler-DeWitt equation in quantum gravity. DeWitt had attempted a standard quantization of Einstein's general relativity and had found, for reasons which are now well understood, that the resulting wave function of the universe must be static. Nothing changes. DeWitt already proposed what has become known as the internal time approach. In a system that contains many degrees of freedom, one is chosen to tell the time. One then determines among all possible configurations of the complete system how the other variables change with the distinguished variable. In the nearly 60 years since DeWitt's paper was published in 1967, there have been innumerable attempts to realize the internal time proposal. The most popular is the one based on quantum entanglement proposed by Don Page and Bill Witters, and I think that was being discussed before my presentation. Indeed, papers are still being published based on the internal idea, but I think it is fair to say that none of them have succeeded. A common feature of all the proposals is their attempt to find relative probabilities for configurations. In contrast, over 25 years ago, as I said at the start, I suggested that the universe should not be described in terms of configurations, but of shapes. In the simplest case of a universe that 3-point particles form, one should not seek probabilities for the shapes and sizes of the triangles, but only their shapes. Thus, I think it is a mistake to look for probabilities for configurations. The probabilities must be for shapes of the universe. Just as I was completing my book, The Janus Point, near the end of 2020, it occurred to me that in a theory of shape probabilities, the variety could serve as a time variable. On the one hand, this was a completely conventional approach that DeWitt had already initiated, but it was novel in two respects. First, instead of just one of the degrees of freedom, a function of them all should define time. The other difference, which is critical and quite different from all the earlier proposals, is that the age, like the variety, is a scale-invariant quantity. This makes a difference that I had never anticipated. Defining the arena of the universe of any finite number of particles with arbitrary mass ratios as the space of all possible shapes they can have, I proposed in my book a time-dependent Schrödinger equation with the variety as the time variable. Two things were immediately clear to me. One was that Planck's constant must be emergent, since it is not scale invariant, but has the dimensions of action. In an approach based on scale-invariant shapes, it can only appear when the rest of the universe defines a scale for a subsystem within it. The other thing that I realized was that the equation must have a unique solution. This relies on two things. First, the variety foliates the considered shape space into isovariety surfaces, but at its center has just one single shape, the one that has the least possible value of the variety. Now, if the equation yields any distribution of the wave function on some isovariety surface, that wave function can be propagated back to the shape with minimal variety. As it approaches that shape, its values must become equal. Otherwise, there will be a singularity at the shape with minimal variety. Apart from the choice of an arbitrary complex number at that initial shape, the solution must be unique. In further discussion with Tim and Flavio Mercati, it became clear that in fact on each isovariety surface, the value of the wave function must be constant. My initial reaction to this was that the theory I had proposed was trivial. However, Tim immediately pointed out that the probabilities which the Born density of quantum mechanics determines depend jointly on the value of the wave function and the appropriate measure in the space on which the wave function is defined. Now, it so happens, and is not widely known, that shapes have probabilities, at least those defined by points in Euclidean space. I will end my talk with saying a little bit about that, for which I show again, as promised, the shape sphere from earlier, now in color. Next slide, please, and with the necessary explanation. Because two internal angles define the shape of a triangle, all possible triangle shapes can be represented as points on the surface of a sphere, which is shown here for the equal mass case. Mirror-reflected triangles have the same longitudes and opposite latitudes. The equilateral triangles are at the poles, and degenerate collinear triangles are on the equator, on which the variety has three saddles and three infinite singularities, corresponding to situations in which the separation between two of the particles divided by their distance to the third tends to zero, and the variety to infinity. Isovariety contours are in white. Now, unlike the Newtonian configuration space, shape space is compact, and the symmetry of the Euclidean group makes it possible to define on it a unique metric, the element of which defines the difference of any two infinitesimally differing triangle shapes. With respect to this metric, the area of the shape sphere is 4 pi, and this permits the definition of probabilities. Suppose certain triangle shapes specified by particular bounds on their angles occupy a small patch of area A on the shape sphere. Then the probability of the set of them will be A divided by 4 pi. In fact, every single question one can ask about the probabilities of n-particle shapes has a unique and unambiguous answer. Now, in quantum mechanics, values of the complex wave function defined in the position representation are converted into positive probabilities for configurations by forming the Born density. What I've just shown you is that something like a Born density for shapes exists without any wave function or Planck's constant. This makes Tim and me wonder whether there is any quantum. This is what scale invariance may imply. If you're interested in finding out more about the arguments for that, I suggest you check out the most recent podcasts at my website, platonia.com. It is time for me to end. Thank you.
Professor, for your talk. I'm afraid that the very last slide didn't come. After this one that is being shown on the screen, this is the last one we had. So I apologize for I didn't get the latest version of your talk. But in any case, we have a few questions for you. And first one here, please.
Can I speak it?
Yeah, you can speak and just speak loud, please.
Hi, Julian. This is a beautiful talk. Well done. You're
Hello,
fantastic
thank you.
always. This is Marina Cortez. I work with Lee. I have two questions. You can answer just one depending on your choice. One of them is the last one. Were you proposing that isovariety surfaces could possibly solve or be a representation for unitarity, for the problem of unitarity in quantum mechanics? And the second question, because I'm a cosmologist, is if you said the CMB can be a good measure of the age of the universe.
Yes. Now, the first question was about unitarity. Now, I would say that if this idea about that there really is no quantum mechanics at all, I would say that each shape exists for itself, and then the only thing that is meaningful within it is the probabilities of subsystems within the totality. There's a huge. We're beginning to. There's somebody in Portugal, Maria Lourenço, who's starting to do calculations with a supercomputer, and you can find all sorts of determine very accurately all sorts of probabilities. You know, what are the probabilities for finding such and such a number of equilateral triangles within many more. So that's so I think if this is right, I think unitarity just loses its meaning. So all of the problems with conservation of unitarity it would just disappear if this is right. You just need the information within one instant and within one shape, and that's very like our immediate experience. Now the question, what was the question again about in cosmology?
Cosmic microwave background is your best estimate for the age of the universe. When you said it's a measure of simultaneity in constant means slicing. Yes.
Now, I was very lucky to interact for 10 years with an Irishman called Neil O'Murrough, he was the first PhD student of Jimmy York, who did that very important work on finding the conformal method for solving the initial value problems in general relativity. And he thought that certainly at a pragmatic level that the constant mean curvature slicing would be very closely aligned with the microwave background. Now, I would think that maybe something really fundamental in that. So altogether, this is if these ideas are right, it completely changes the way we must think about physics and the universe, because we must no longer think that motion is on has the same ontological status as position, which is really suggested by the result of DeWitt long ago, that position is fundamental. And in fact, if you don't have positions of objects relative to each other, there's no way that you can determine any motion, how they change. So I have to say, this makes me very suspicious about the uncertainty principle in quantum mechanics, which is often just presented for a single particle effectively in Newton's absolute space. I just find that very suspicious.
Thank you. Other questions?
Hi, Julian. Thank you very much for your talk. I was wondering if you could say a little bit more about what you find unsatisfactory from these internal time or internal clock approaches, and maybe how what you're proposing differs. Because my understanding is you are starting with a set of constraints and then trying to identify a time variable. And I was just wondering if you could say more about that.
Yes, a little bit. Well, I have actually now, David Deutsch in Oxford, as you probably know, is very keen on the internal time approach. And I have interacted with two people who worked with him, and they did doctorates with them. One is, what are the names? I'm getting terrible as I get older with remembering names. One is Samuel Kuipers, and the other is Simone. He's Italian, Simone, and I'm afraid I forget his surname. Now, I discussed with them one problem, which is how that the clock in the original formulation of Page and Waters, the clock, there's no way, the clock and the universe are completely distinct. There's no coupling between them. So the problem is, how can people within the universe read the clock? And that stimulated Simone in quite a long paper, which is on the web, to show how that could be done. I'm not very good on technical things, and I have to say I haven't looked at it. It's a pretty technical paper, but he certainly has addressed that in you. Then I put another problem to him, which is, where is the clock face? So if you say that 1 degree of freedom is the moving hand, you've got to have a clock face to see where it's moved. Now, let me remind you of the concept of ephemeris time in astronomy. When in the 1890s, the astronomers found that there seemed to be an anomalous acceleration of the motion of the moon, they suspected it was due to internal processes in the Earth changing its rotation period. So they then treated just the Earth, Sun, and Moon to a good approximation, and said that you should choose the time variable so that Newton's second law is satisfied for those three celestial bodies. So in that case, it's very, very beautiful. The moon is the moving hand of the clock, and the fixed stars are the clock face. So what I was asking from Simone and Sam was, where is the clock face? So I'm not quite sure whether an answer to that is there, but I think this is very, very fundamental, that you just must. If I can't imagine seeing that with my eyes, I have problems.
Maybe we can talk a little bit about that offline. Maybe there are resolutions to those objections. I mean, for example, to the first point, the fact that the joint state of the clock in the system satisfies a constraint establishes correlations between the clock and the system. So you're right, there's not an interaction Hamiltonian necessarily in the constraint, but observables on the clock and system do become correlated by imposing constraints. But to your second objection, I'll think a little bit more about that. But thank you.
Yes. No, pleasure. I mean, the problem. I mean, I just have to say, I know it sounds absolutely outrageous, and even people very sympathetic to my ideas begin to shake their heads when I say it. But I think one really might ask, is there really any quantum mechanics? Now, that sounds completely impossible, but I would put it to people, to everybody listening. I think it's quite extraordinary how three-dimensional scale invariance has been ignored. It's the only place I know, I'll be glad if anybody in Brazil can tell me, listening, the only place I know where it has come to play a significant role is the Newtonian n-body problem. They couldn't avoid it because otherwise these, what they call total collision solutions, or there's also ones called parabolic escape, could not be described. And this quantity that I've called the variety comes in absolutely critically. But I'm not sure that they've sort of come out shouting, saying scale invariance is the fundamental symmetry of the universe, which is what I'm beginning to suggest, because I'm sitting at my desk looking at a walnut tree outside, and if everything was just multiplied by a common factor, there would be no change. So information is scale invariant. This is beautifully illustrated by Chinese characters. Whatever their size, their meaning remains the same. So I think the very fact that we can talk meaningfully about things, underlying that is scale invariance.
Any more questions? So, Professor, I think we thank you for your talk, and we're going to end right now.
All right.
Thank you very much.
I have one question I was not going to ask, because Julian, it is simple, and if you're tired, don't answer. The notion of variety as a measure, how can we reconcile that with some interactions that have negative specific heat and positive specific heat? It seems that some interactions decrease variety and some increase variety in evolution, like gravity and thermal interactions.
Yeah, there's no. It's perfectly possible that in a localized region the variety can go down, but overall that's still compatible with it overall increasing.
Yes. Yes. Okay. Thank you.
Yeah, I mean it's just that if, I mean, I illustrate almost everything with just triangles. If you have triangles, the minimal variety is the equilateral triangle. And you just go on, if you want to increase the variety, you just make it ever more pointed. It just goes on forever. You can do just the same with four particles. The regular tetrahedron has the absolute minimum. So that you can decrease the variety of, say, three of the points. It's perfectly possible to do that.
Yeah.
But if this is right, it requires a complete change in the way we think about things. Everything that we experience, it's a very rigorous. It requires great, strict rigor. Everything we experience must be correlated with change in the distribution of particles. Now, in some ways, that's very easy. If I touch an object and find it's very hot, then I'll know that the separations between the particles in that body are somewhat greater than if the temperature was a bit lower, if there's one next door to it. So that's the sort of way I'm now thinking, and it's. Let me also say another thing in this. I recently read, I only got halfway through it, but I recently read the famous Latin poem by Lucretius on the nature of things, De Rerum Natura. And what comes clear from that is, well, pretty clear if he's a good guide to the ancient atomists 3 centuries before him. What they were really trying to understand was shapes. Why all sheep have the same shape, why children look like their parents. And so for that, they postulated that everything is made of these atoms, which are shapes, they're solids, indivisible solids with different shapes. And if you think about it, the first sort of theorizing that humans seem to have done was trying to explain the shapes that the stars in the sky form. That's why I mentioned the constellation Orion near the start of my talk. So they created these beautiful stories of why, the beautiful story of Orpheus and Eurydice, and so his harp is there in the sky. So I think there's a lot to be said for going back to the original ideas. And let me also say in this connection, whether anybody knows it, what is the etymology of the word create? It's nothing to do with creatio ex nihilo. It comes from the Proto-Indo-Germanic word ker, meaning to grow. And this is exactly what you can describe very precisely with this notion of variety. It starts from maximal, but not perfect uniformity. By the way, also, I may say that all of the problems that you have in general relativity with the creation of structure, macroscopic structures, and where they come from, this is what led to the Harrison-Zeldovich prediction, suggestion of a scale invariant spectrum, and then has been taken up in inflation, where there's very great difficulty in saying how inflation starts. It does work wonderfully once it's started and then come to an end somehow or other, but there's a lot of very difficult bits in between while, and that is just to show, explain how seeds, inhomogeneities, which become the seeds for macroscopic structures form. Well, they're from the word go in the Newtonian n-body problem. They're there. You saw them in those, that where I showed the two that Manuel in Paris discovered. The one on the left is not exactly uniform. The separations are greater at the edge than at the center, but that's just because it's done in 2 dimensions. That doesn't happen in 3 dimensions. But there's still slight subtle differences. And then the minute you go to the one on the right that I showed you, it's incredible, the things. Now those structures are all there, and out of them they can lead on to galaxies, whatever you like. And that's all done without inflation, not the slightest problem in the Newtonian n-body problem. So I'm not alone in being suspicious about inflation.
We have one last question, Professor.
Hi, Julian. It's Henrique. Thank you so much for the great talk, as usual. I just wanted to pick up on this last remark that you made about the Born density. I think, one might be able to recover a Born. You want me to go?
No, not you.
One may be able to recover the Born density, but I would still worry about things like interference. How could you? Well, when we talk about quantum mechanics, yes, when states have decohered, everything has decohered already, the classical histories have decohered, then I agree that it would be enough to just talk about the Born density. But quantum mechanics has other regimes as well, a lot of interference effects that are very important. And for those, it doesn't suffice to just get the Born density. And for those, which is where one would say the uncertainty relations come from, for those, I would think that getting back the Born density is not enough.
Well, I agree there's a lot of work to be done. Let me say, though, that if these ideas are right, first of all, it means that physics must no longer be treated in a reductionist manner. It must be treated as holistically. So the whole of these shapes that I showed you, They are completely holistic. They are determined just by the mass ratios of the particles. Nothing else determines these things. So that's pretty remarkable. So there's and so you can see very often where, if you I didn't show it, but there was a numerical study made where they had particles heavier than other ones, and the heavy particles stopped any. You could see it's all comes out of the statistics of getting the variety right. The light particles can't get too close to the heavy one. They're kept away from it. So Tim Kozlowski and I have coined the expression shape conditionals, so that if you have a certain condition, a certain part of the total shape of the whole universe takes a particular form, then you may expect something rather special in its immediate vicinity. Now, I did some time ago look at the very first two-slit experiment, which was made by Thomas Young, amazing man, in 1800. Now, that was an incredibly special experimental setup, terribly delicately done. So perhaps one shouldn't be surprised if something a bit special happens next to it. I mean, just to make a ridiculous thing, if you see a baby kangaroo hopping around, it's pretty likely you'll see a mother kangaroo not far away. So maybe these interference fringes are nothing to do with are nothing to do with the wave function splitting into two and going through the two things, because there's a. Let me also say, quantum mechanics. What were they trying? There's an alternative explanation that could have been sought for quantum mechanics. They were basically trying to explain structures in photographs. All the evidence for quantum mechanics, in the sort of Copenhagen way of thinking about it, is essentially literally in photographs or generalized photographs. It's all, and that is altogether in just distributions of fermions. It's not in distributions of photons. It's in distributions of fermions. So if you can find an explanation for the distribution of the fermions, then maybe you don't need all of this thing. So maybe just imagine all the shapes at one particular value of the complexity, and a divinity who can take a photograph of them at that value of the variety or complexity. Now, there are probabilities for those shapes, and it may well be that in one of them you find, in a very small part of one of those shapes, you find actually the image of the laboratory with the experimentalists, the cloud chamber, and the photograph it is taken. And the explanation is all there because of the holistic nature of the shape, that there is an alternative to it. And one more thing I may say, in Heisenberg's paper of 1925, when he created wave mechanics, he said that the single sentence in the abstract is an attempt will be made to create a quantum formalism that relies solely on quantities that are in principle observable. That was a very Machian way of thinking about it. But when you actually look and see what they were not what I would call things that are directly observable. They were energy differences and transition probabilities. Now, these are data obtained at second hand. When Newton saw the rainbow on the wooden shutter of his room in Cambridge, his retinas were correlated with subtle changes in the distribution of fermions on the wooden surface. He didn't see light. We don't see light, we see things. And that data that Heisenberg used to derive matrix mechanics, it's not raw data, but processed data. Now we know processed food is bad for your health, so I'm suggesting that processed data are bad for theory. Well, I should go back to the barest information is encoded in distributions of fermions, as far as I can see, and that's very far removed from wave functions and curved space and all those things like that. I think all of that might just be adding a whole lot of essentially Ptolemaic epicycles to the raw data.
Okay, Professor. I think we must wrap up right now. Thank you very much.
Okay, yes, fair enough. I sounded off.